morning, dear students. Welcome back to my chemistry class. So I am continuing the Ionic Equilibria. Today I am going to discuss about the hydrolysis of the salt, and thereby wish to derive the relation between the hydrolysis constant K of the salt with respect to Ka or Kb through Kw. Okay. Kh is the hydrolysis constant of the salt. Ka is the dissociation constant or ionization constant of the weak acid. Kb is the ionization constant or dissociation constant of weak base. Kw is the ionic product of water. So there exists a relation between Kh with respect to Ka or Kb as the cases. Okay, as the cases through Kw. So we have to derive that expression. So before that, we have to look into what is the salt hydrolysis and what is the nature of the aqueous solution of the salt due to the hydrolysis. And we have to explain that peculiar behavior of the aqueous solution of a salt. After that, we can pass on to the relation. The salt, as you know, salt is a neutralization product between an acid and a base. Okay, salt is a compound or is a substance that is produced as a result of the neutralization between an acid and a base. Example, all of you know that sodium chloride, calcium chloride, sodium sulfate, calcium sulfate. Okay, generally we can aluminium chloride, ferric chloride, aluminium sulfate, aluminium phosphate, all these are salts. Salts are generally classified, generally expressed by the term that is B, that is called AB, A plus B minus. Okay, A plus B minus, where A plus part is assumed to be obtained from the acid, while B minus part is assumed to be obtained from the base. Okay, I will B and B. Okay, B. Or we have to say that salt is generally represented by. Okay, as you can give any symbol. As salt is a neutralization product obtained from the acid and base, a salt has generally two parts. One is a cation and other is the anion. Okay. A salt is a species which contains cation and anion. The peculiarity of salt is that when dissolved in water, it undergoes complete ionization. That is another peculiarity of the salt. All types of salt undergo complete, almost full dissociation or ionization in the solution. Then, based on the nature of the acidic cation and the anion, or based on the nature of the anion or acid or base from which the salt is derived, we can classify salt into four categories. Okay, salts can be generally classified into four categories. One is, so four types of salt. Four types of salt. One is salt of strong acid and strong base. Salt of strong acid and strong base. Okay, these are the sort of simply derived from the neutralization reaction between strong acid and strong base, like HCl and NaOH. We have NaCl. You have NaCl. So, okay, and KCl, NaCl, Na2SO4, etc. And as to the salt of strong acid and weak base. Sort of strong, okay, weak acid and strong base. Sort of weak acid and strong base like acetic acid and NaOH, that is sodium acetate, CH3COON. Okay, CH3CON. And next example, sodium benzoate. Sodium benzoate. CH3 C6H5COON. Sodium formidated. All these are example of weak acid, salt of weak acid and a strong base. And third is salt of reverse. That is strong acids against and its weak base. Like strong acids is HCl against a weak base like ammonium hydroxide. So it is an example of ammonium chloride, ammonium carbonate, etc. So salt between ammonium hydroxide and ammonium sulfate, ammonium chloride and ammonium sulfate, SO4 tri. It's what SO4. And it's what twice ammonium sulfate or ammonium nitrate. What is an example of salt of strong acid against a strong weak base? And finally, the salt of both weak acids and weak base, like ammonium, yes, that is ammonium acetate, that is CH3 COONH for ammonium acetate, and ammonium carbonate, NH4 twice CO3. So between ammonium hydroxide and carbonic acid, this is between ammonium hydroxide and acetic acid, etc. Ammonium formate, etc. All these are examples. So there are, we have to generally, I have said, there are salts are neutralization product between an acid and a base, and it consists of two parts. One is a cation and other is the anion. That part derived from the base acting as the cation, while that part derived from the acid acting as the anion generally. So a salt generally has two parts. One is cation, positive part, and other is the negative part, anion. And then salt always exists completely dissociated, or ionized in their aqueous solution or dissolved in the water. That is a peculiarity. It has, since it is considered as a neutralization product, the aqueous solution of a salt is expected to be neutral. We can speculate that the aqueous solution of a salt may be expected to be neutral in nature, but it is not actually the case. The aqueous solution of an acid may be an acidic or basic, or in some time it may be neutral. That depends on the nature of the salt, or that depends on the cationic or anionic part of the salt. The aqueous solution of a salt may be not always neutral. It may be acidic in some cases, or it may be basic in some cases, and it may be neutral in certain other cases. So we will explain the behavior of the aqueous solution of the salt. So what is hydrolysis? Okay. It is due to the peculiar behavior why the aqueous solution of an salt is not neutral in nature. It may be either acidic or basic, or only in certain cases only it is neutral. It is due to a peculiar phenomenon called hydrolysis. So you have to pass on to the hydrolysis of a salt. The hydrolysis of a salt, that is the process or the interaction between of the cation and the anion of the salt with the water molecule to produce acid and a base in the salt in the solution is called hydrolysis. So the hydrolysis is the process. Hydrolysis is the process of the interaction of the cation and the anion of the salt with the water molecule to produce acid and base in the aqueous solution. So the cation and anion part, interaction of the cation and the anion with water molecule to produce acid and a base in their solution. Okay, that is Ba. Okay, the salt Ba plus H2. We have to use the ionized is completely ionized, B plus A minus. They completely ionized or dissociate in the water. So again, next to the ionized species, so it will undergo react the cation and anion interact with the water, giving B plus OH minus plus HA. This is a situation. This is acid and this is base. And this reaction is typically called hydrolysis. Okay. The process of the interaction of the cation and the anion with the water molecule to produce acid and a base in their aqueous solution is called hydrolysis. So depending on the nature of the hydrolysis, an aqueous salt solution may be either acidic or basic, or some cases it is neutral. So you have to pass on to the cases. I have mentioned about 4 types of the salt. Out of the first category, the first categories are the salt of strong acid and strong bases, like NaCl, KCl, Na2SO4, etc. that do not undergo hydrolysis at all. Instead, they undergo a process called hydration. When dissolved in water, but in spite of that, the system is neutral. Aqueous solution is neutral. So the case number 1, that is the salt of like NaCl, KCl, okay, etc., or Na2SO4, etc., or KNO3, all these type of salt do not undergo hydrolysis. Instead they undergo a process called hydration. That is a process in which the cation and the anion is caged by water molecule. The caging of the cation and anion is solved by large number of water molecule in a suitable orientation. Okay, that is called hydration. That phenomenon actually takes place. The cation is surrounded by water molecule with respect to oxygen facing towards it, and anion is surrounded by the large number of water molecule with the H plus ion of water molecule orienting or facing towards it, and that is called a kind of caging of cation and anion. And this is process called hydration that results in the dissolution of that particular substance in the water. But the system is neutral. Like NaCl plus H2O giving NaOH aqua plus NaCl aqua plus HCl aqua. Okay. This is a peculiar situation, Cl minus, and it is both are strongly acidic, so it is neutral. Oh, sorry. In this case, we have to say that NaCl plus H2O, actually they are such a manner that Na plus is surrounded by water molecule. Na plus is surrounded by water molecule in large number. So that they are not actually undergoing hydrolysis. Instead they undergo the NaCl undergoing water, Na plus H2O aqua giving Na plus aqua giving NaCl plus aqua or NaCl aqua, so that it will give Na plus aqua plus Cl minus aqua. This is a situation. Okay, this is called hydration. This process is called hydration. So what you have to remember, you have to note in this case that the salt of strong acid and strong bases, as NaCl, would not undergo hydrolysis. Instead, they undergo a process for hydration. So that is the cation and anion is surrounded by large number of water molecules. But the case 2, the salt of a weak acid and a strong base, like case 2, sodium acetate, CH3, COONA, C6H5COOK, etc. And this type of salt of the weak acid and a strong base, they when dissolved in the water undergo hydrolysis. They react with the water molecule, they undergo hydrolysis, so that a weak acid and a strong base is produced. So the salt of a weak acid and a strong base undergo hydrolysis with the water molecule, that is CH3COONA, react with the water molecule, interacts, the cation anion of the salt interact with the water molecule to produce an acid CH3COOH plus a base NaOH. The peculiarity of the product is that we get acid and a base. So weak acid, acetic acid is a weak acid, NaOH is a strong base. Since acetic acid is a weak acid, it only undergo feeble ionization. It does undergo only feeble ionization. Feebly ionized. Feebly ionized to CH3, CO minus plus H plus, only feeble ionization. Feeble ionization. But then since it is a strong base, it is strong electrolyte, it is a weak electrolyte, hence undergo feeble ionization, so the number of H plus ion is very few in the aqueous solution. But anyway, strong base, it undergo full ionization to Na plus and OH minus. This is the situation. There is strong electrolyte. It is a weak electrolyte, undergo feeble ionization. So, in the aqueous solution, the concentration of OH minus ion is much greater than H plus ion, therefore it is basic in nature. So the aqueous solution of sodium acetate is basic in nature because the concentration of OH minus ion is much greater than the concentration of the H plus ion, because the product acetic acid is a weak electrolyte, is feebly ionizable, but the product energy is a strong electrolyte, is a strong base, so it undergo full ionization, so the concentration of OH minus is much greater than H plus ion, so it is basic in nature. But case 3, that is the salt of strong acid against a weak base, like strong acid against weak ammonium chloride, ammonium sulfate, etc., ammonium sulfate, ammonium nitrate, okay, etc. This type of salt, when undergo hydrolysis with the water, so when react with water, it undergo hydrolysis to forms, it undergo hydrolysis with water molecule to form a weak base, ammonium hydroxide, a weak base, plus a strong salt HCl. It's a weak base, but this is a strong acid. Since it is a weak base, it is a weak electrolyte, it will undergo only partial ionization. It will undergo partial ionization to NH4 plus and OH minus ion feeble. It's a feeble ionization. But HCl, since it is a strong acid or strong electrolyte, it undergo full ionization, complete ionization to H plus and Cl minus. Therefore, the concentration of H plus ion is much greater than OH minus ion. So, H plus ion in the solution is much greater than OH minus ion, so it is acidic in nature. So, the aqueous solution or the aqueous salt solution of ammonium chloride, that is sort of weak acid and strong weak base and strong acid, is always acidic in nature. It is of this fact. Then finally, the salt of weak acid and a weak base. That is salt of weak acid and a weak base like ammonium acetate. That is CH3COONH4. Ammonium acetate. Then ammonium carbonate. That is the salt of carbonic acid and ammonium hydroxide. All this salt. The aqueous solution of the weak acid and the weak base is generally neutral, or they are slightly acidic or slightly basic, or generally they are neutral, because the salt solution on hydrolysis CH3CONH4 react with the water molecule, okay, and interact with the water molecule giving the product of weak acid and weak base. CH3COOH. CH3COOH plus a corresponding weak base, that is ammonium hydroxide. It's a weak acid. Weak acid, here also a weak base. So both are weak electrolyte. Since the product of the hydrolysis are weak acid and weak bases, both are weak electrolyte, they exist only partially ionizable. They exist only partially ionizable in their solution. So CH3, CO minus, H plus, NH4 plus OH minus, and they will undergo partial ionization to give H2. Okay. So what is, since they are only partially ionizable, the concentration of H plus ion, is almost equal to the concentration of OH minus ion. Therefore, the aqueous system is neutral in behavior. Okay, that's the situation. Then we have to pass on to the relation between KH. Hydrolysis constant KH of a salt with respect to through K and Kb through Kw. So to consider the salts, or to derive this expression for three cases, sort of strong acid and weak base, weak acid and a strong base, weak acid and a strong base, and sort of weak acid and weak base. Case 1. The relation between KH of a salt with respect to K and salt of a weak acid and strong base. Consider a typical example as CH3COON. Consider sodium acetate, strong base. Okay, sodium acetate as a typical case in this case. Okay, sort of a weak acid, strong acid, and okay, case 1, sort of a strong acid and a weak strong base. Okay, I have to explain. So hydrolysis constant, a weak base and a strong base like a CH3COI. Consider a typical salt like a sodium acetate. CH3CONA plus H2 giving, okay, this is completely ionizable, CH3CO minus and Na plus H2 giving, the salt is, the product is CH3COOH plus NaOH. Again, this is completely ionizable. Since a strong electrolyte is completely ionizable, so they will cancel each other. So the or we can write this equilibrium can be written as CH3CO minus plus H2O reversibly gives CH3COH plus OH minus. This is the hydrolysis equilibrium. This is the hydrolytic equilibrium of this type of salt. That is CH3CO minus plus H2O giving CH3COH plus OH minus at equilibrium. Therefore, K, the equilibrium constant K is equal to concentration of CH3COH into concentration of OH minus here at equilibrium divided by the concentration of CH3CO minus into concentration of H2O. But you know that this water, concentration of water, since it is a solvent, it is assumed to be practically constant. So K into concentration of H2O. Concentration H2O is a constant. Since water is a solvent, its concentration is practically constant. So K into this constant is a new constant that is equal to KH. KH is equal to CH3COH into OH minus divided by CH3COO minus. This is our equation. Okay, this is the equation number 1. So the hydrolysis constant KH of such a salt, weak acid and strong base, salt is is equal to concentration of weak acid into concentration of base divided by the concentration of unionized that is anion of this acid. Okay, you look. Okay, look at this sketch. Then, when we are considering the aqueous solution of the salt, there is another equilibrium or the weak acid. You know that in the solution there is an equilibrium of the weak acid. There is another equilibrium with respect to the weak acid. Okay, considering the weak acid, there exists another equilibrium in water for the weak acid or with respect to the weak acid as CH3 COOH plus H2O giving left more towards left. Okay, so is giving CH3 CO minus plus H3O plus. This is the situation. This is equation number 2. So this is the equilibrium reaction, the equilibrium reaction of the with respect to weak acid. Therefore, we have the equilibrium constant K for the weak acid. That is equilibrium constant K for the weak acid is K. I am going to write directly. This is assuming this as a constant. Assuming the concentration H2 as a constant, I can write K is equal to concentration of CH3 CO minus into H3O plus divided by concentration of undissociated acetic acid. This equation. This is our equation number 2. Okay. This is merely the hydrolysis equilibrium, and this as equation number 2. You give to us for the constant K. So we have equation number 1 KH is this, and equation number 2 Ka is CH3CO minus into H3O plus divided by CH3COH. And finally, we have, that is, in aqueous system, there is an equilibrium between the ions of the water molecule, that is H plus, H3O plus and OH minus, that is Kw. So, the Kw in water aqueous system, there is an equilibrium between the ions of the water, that is Kw is equal to H3O plus into OH minus. This is equation number 3. So we have 3 equilibrium constants. One is KH, the hydrolysis constant of water, is equation number 1. And we have the dissociation constant, ionization constant of weak acid, Ka, as equation number 2. And we have Kw, the ionization constant of water, Kw as H3O plus into OH minus. You divide equation 3 by 2. Equation 3 divided by 2. Okay, I am writing this equation 3 divided by equation 2. That is equal to 3 by 2. Kw, I hope that you can see here, Kw by Kh. Kw by K is equal to Kw by, that is H3O plus into OH minus divided by this part, CH3 CO minus into H3O plus divided by CH3COH. So this comes here. That is equal to CH3COH into OH minus divided by CH3CO minus. You look into this equation. This equation is equal to this. So Kw by K is CH3COH into OH minus divided by CH3CO minus. and that is equal to KH. Look, therefore we can write. So equation number 4. This equation number 4 is now equal to 4. Equation 4 is equal to equation 1. That means KH is equal to KW by K. So that is the relation we have to study. So the hydrolysis constant of a salt of a weak acid and a strong base is equal to any product of water divided by the dissociation constant of the weak acid. That is KH is equal to KW by KH. Okay, similarly, the second case of strong acid and a weak base salt, the salt of a strong acid and a weak base like ammonium chloride, you will get KH is equal to KW by KB. You can derive that expression. Okay. So we have the equation like this. Then we have to pass on to derive the relation between the degree of hydrolysis, pH, etc. How it is connected. That the relation between the hydrolysis constant of the salt, degree of hydrolysis of the salt, how it is related, we have to degree of hydrolysis. Degree of hydrolysis, that is alpha, then, and pH of the solution. Okay, we can have the equation. We can have the equation that is salt the cases, that is your CH3 COO minus plus H2 reversibly gives CH3 COOH plus OH minus, as you know. This is our equation. The anisotropy equilibrium of the salt equation is like this. Okay. So such a salt is like this. That is CH3COH plus OH minus. Let C moles per liter be the initial concentration of the weak acid. So this is C moles per liter. So it is zero. This is zero concentration. At equilibrium. So suppose alpha is the degree of dissociation. Suppose alpha is the degree of dissociation at equilibrium. So you look at, suppose alpha is the degree of dissociation at equilibrium. We have C into 1 minus alpha mole of acetate ion is a constant. C alpha moles of acetate ion and C alpha moles of OH minus ion. Therefore, at equilibrium, the ionicity equilibrium, the salt hydrolysis equilibrium contained C into 1 minus alpha moles of acetate ion, C alpha of the unionized salt, while C alpha and C alpha moles of acetic acid and hydrous ion. So we have the equation that is in terms of KH. Okay, we have the equilibrium constant KH is equal to, as you know that, KH is already known, CH3COH into OH minus divided by CH3CO minus. So we have the equation C alpha into C alpha by C into 1 minus alpha, that is equal to C square alpha square. C square alpha square by C into 1 minus alpha, that is equal to C alpha square by 1 minus alpha. Since alpha is very small compared to unity, alpha is very, very small compared to 1, it can be neglected. The denominator C of KH is equal to C alpha square. C alpha square. So alpha is equal to square root of KH by C. So that is the situation. So alpha is equal to square root of KH by C. So we have the equation alpha, the degree of dissociation of the salt, is equal to square root of Kh by C, where K is the hydrolysis constant of the salt, that is equal to Kw by K. Therefore, alpha is equal to Kh is Kw by Ka. Okay, K by square root of K by this equation. This is our equation. But as you know, what is alpha? Alpha we have now, we know that what is the hydrosol. The aqueous salt equation is, that is CH3 CO minus plus H2O giving CH3 CO minus plus OH minus. So in this equation you always know that is the concentration of OH minus ion. OH minus ion concentration is equal to C alpha. So in the aqueous solution, the concentration of hydroxyl ion is C alpha. Okay. Therefore, concentration of hydronium ion is Kw by OH minus. Okay. That is equal to Kw by C alpha. This is our equation. Kw by C alpha. So we can have the equation. The hydronium ion concentration is Kw by C alpha. The concentration of hydronium ion is Kw by C alpha. What is C alpha? As you know that? C alpha, but alpha, putting alpha here. Alpha is equal to square root of alpha. Alpha is equal to, okay, alpha is equal to square root of Kh by C. Okay, alpha is equal to, yes, alpha is equal to square root of Kw by K by C. So putting this value here, alpha square root of Kw by Ka by C. In this equation we have S3O plus is equal to Kw divided by C into alpha square root of Kw by Ka by C. So this equation, it is numerically, it is mathematically multiplied with that is equal to Kw by, okay, square root of C, and multiply here square root of C, so that C get cancelled here, so comes square root of C here. Okay, square root of C into square root of C. Okay, like that. So we have Kw by Ka into square root of C. Okay, like this. This is our equation. Mathematically, the equation comes like that. C into like that. C into square root of C. Okay, square root of C. Oh, next. Square root of C. C into square root of C divided by K by square root of C into square root of C. So that square root of C into square root of C into 1C cut here. Okay, we have square root. So we have like this. C into lines. This equation. So we have the equation Kw by Ka into C. That is equal to, again we can written as here Kw square root of Kw. Okay, here Kw now disappears. So we have square root of Kw, okay, into Ka by C, I think. It by square root of C. Okay, this mathematical work, K comes here, and again this is Kw plus U together. Now the equation now become like this. So on numerical simplification, now the equation S3O plus ion concentration is equal to square root of Kw Ka by C, square root of the whole square root of Kw into Ka by C. This is our situation. So you take the logarithm. Log H3O plus is equal to log square root of, square root means KW Ka by C, the whole raised to half. Okay. And you know the log H3O plus is pH. Log H3O plus is pH. So we have the equation. pH. pH is equal to half log. That is wrong. Yes, minus log. Okay. Half into. Minus log H3O plus is minus log KW K by C into the half into minus log. Okay, minus log. You are opening this minus log. Half into minus log KW minus log Ka. Okay, minus plus. Okay, minus log minus C, log C, that is equal to plus log C raised to half. Okay, like this, half. So we have the equation like this. That is equal to, okay, I'm good. That is pH is equal to half into minus log KW is PKW. That is equal to PKW minus log K, minus log Ka is PK. So this time minus log Ka is PK plus PKA plus log C. That is equal to PKW is 14. That is half into 14 plus PKA plus log C. That is equal to 7. Half into 14, that is equal to 7 plus half PKA. Okay, half 7 plus half PKA plus half log C. So we have the equation Ka plus equation now become half log C, I think. Half into, there is a numerical correction here. Yes. Half log C, half PK plus half log C. So the equation is now done. Okay, and now you put like this. So the pH of such a solution is pH is equal to 7 plus half into pKa plus log C. That's all. So if it's possible, you can derive this equation. Otherwise, you have to derive this part also. That is equal to KH is equal to KW by Ka. Okay. Or alpha is equal to square root of KW by Ka by C. That's all. So thank you very much. So time being, I am going to wind up the class. So next is the same expression for weak acid and that is strong acid and a weak base like ammonium chloride. I hope that you can try. And finally we got to derive weak acid and weak base like ammonium acetate. Okay.